Students, in today's lecture we are going to see some different properties of outer measure. So we start with the proposition that the outer measure of an interval is its length. We know that there are different types of intervals. First are bounded intervals and second one is unbounded intervals. So in bounded intervals there are closed intervals, open intervals and semi-open or semi-closed intervals. So to prove the outer measure of an interval is its length, we see the different cases. So first we will see for the bounded interval its outer measure its length. So let's start. So we begin with the case of closed and bounded interval closed AB, and I have to show that outer measure of that interval is its length. And what is length of bounded interval? Length of bounded interval is b minus a. So my claim is outer measure of closed AB equal to b minus a. So first I choose epsilon greater than 0. Then the open interval a minus epsilon and b plus epsilon contains closed AB. That is, if I consider closed interval AB for epsilon greater than 0, if I subtract epsilon from point A, then I get back, and here I get a minus epsilon. If I add epsilon to b, I get a point here which is b plus epsilon. So this interval a minus epsilon and b plus epsilon forms a covering for closed AB, and we know that if there is a covering, then outer measure of an interval is equal to infimum of sum of length of that interval which covers given set. But here is only one interval which cover closed AB, so infimum of length of this interval. So what is infimum of length of this interval? Length of interval, this a minus epsilon and b plus epsilon is bounded set, so its length is the difference between its end point, and as epsilon is arbitrary and here is a plus sign, so if we neglect these two epsilon, then we get inequality. After measure of closed AB is less equal b minus a. Now according to my claim, if I show outer measure of closed AB is greater equal b minus a, then it is proven that outer measure of closed AB is less equal b minus a, and thus we get outer measure of closed AB is equal to b minus a. So my claim is to prove that outer measure of closed AB is greater equal b minus a. So for this we show that what is outer measure of closed AB? Outer measure is infimum of sum of length of ik greater equal b minus a. So if infimum is greater equal b minus a, then sum of each interval is also greater equal b minus a. So my claim reduces to from this to this, that outer measure of sum of length of ik is greater equal b minus a. Where what is ik? Ik is a countable collection of open and bounded intervals covering closed AB. But we know that Hine-Borel theorem states that if we consider any collection for closed AB, then it also have a finite subcollection that also covers closed AB. That is, if I1, I2, Ik up to so on there are infinite intervals which covers closed AB, then we consider some finite collection among that interval that also covers closed AB. So I choose a natural number small n for which ik k varies from 1 to n covers closed AB. That is I1, I2 up to so on ik covers n covers closed AB. So my claim is reduces from infinite interval, I choose finite interval. So it is sufficient to prove that sum of length of ik, where k varies from 1 to n, is greater equal b minus a. This is my required claim. So to prove this, as we know that ik is open covering for closed AB, so union of ik also contains a, so a belongs to union of ik, and as a belongs to union of ik, a belongs to ik for some k. So as a belongs to any of the interval, I choose such interval and label it as a a1 b1. So a belongs to, I consider interval a1 and b1 such that a belongs to that a1 b1. But where is b1? b1 is either less than b or it is either greater than b. So here we come across two cases, if b1 greater equal b and b1 less equal b. as a1 less than a less than b1, because a belongs to a1 b1. Now if b1 is greater equal b, what if b1 is greater equal b, then b1 is some here. So this interval a1 b1 forms a covering for closed ab, and there is maybe another set which also covers closed ab. So I take sum of length of ik is greater than or equal to b1 minus a1, and it is trivially proved that it is strictly greater than b minus a. Now the second case, if b1 is less than or equal to b, so here is a1. If b1 is less equal b, then here is b1, and in that case I consider, so b1 is less than b in this collection, then I take ik. Among this collection I consider one of the interval which also contains b1, so I say it a2, and here is some b2. Again we came across with two different cases, that b2 is less than b or b2 is greater than b. This b2 is maybe here or here. So again we come with different cases. So if b1 is less equal b, then there is an intervals, we label it as a2 b2 in the collection ik, distinct from a1 b1, for which b1 belongs to that open interval, and this is ordered relation because b1 belongs to a2 b2, b1 lies between a2 and b2. So if b2 is greater than b, that is if b2 is here, then what we get, sum of length of ik is, there are two intervals. Now if b2 is greater than b, then there are two intervals a1 b1 a2 b2 which covers closed ab. There may be other intervals, so sum of length of that interval is greater equal, what is sum of first interval and second interval, b2 minus a2 plus b1 minus a1, and which is strictly greater than b minus a, because it is a cover for b minus a, sorry, closed ab. So if we continue the process of selection until it terminate. Why this process is terminate? Because I have some finite intervals, so this process is absolutely terminate somewhere. So I continue the process till the sequence of ik are terminate. So since the process is terminating, sum of length of ik is greater than or equal to, we continue this result, so sum of length of ik is greater than or equal to bn minus an plus bn minus 1, and which is strictly greater than b minus a. These bn, an, bn minus 1, an minus 1 are all real numbers, and we know that real numbers are associative, so we can shift this bracket. So I only rearrange this in the form of this and this inequality, which is strictly greater than b minus a. So what I get, sum of length of ik, k varies from 1 to n, is greater equal b minus a. What it gives? It gives that if I take infimum, then infimum is also greater equal b minus a. And what is infimum of sum of length of ik, where k varies from 1 to n? Infimum is outer measure, so outer measure is greater equal b minus a. So here we prove that outer measure is greater equal b minus a. Previously we proved that outer measure is less equal b minus a, and therefore from equation 1 and 2 we say that outer measure of closed interval is b minus a. So this is for bounded interval. Now if I consider any other interval, okay, so we consider the case for closed interval. Now if we consider any bounded interval, then there exists for epsilon greater than 0, there exists closed and bounded set j1 and j2 such that I is contained in j1 and I is contains in j2. That is, if I consider any other interval other than closed ab, then I choose two bounded intervals j1 j2 such that j1 is contained in I and I is contained in j2. So what is length of I? Length of I minus epsilon is less than length of j1, and length of j2 is less than length of I plus epsilon. So what is length of j1? j1 is interval, so its length is its outer measure, and j2 is also interval, so its interval's length is outer measure of j2. So if we rearrange this in the form of outer measure, we say that outer measure of I is equal to, then we will see that outer measure of I is equal to length of I. So this is the case of bounded intervals. So this is hold for bounded interval. Now if the interval is unbounded, then what we do? So for unbounded intervals, so take I be any unbounded interval, then for each natural number n, here is a construction. So for each natural number n, there is an interval j containing I with length of j equal to n. So the construction is simply like that. There is an interval j with each natural number's length. That is, there is an interval j which length 1, j with length 2, j with length 3, j with length 4 up to so on. So there is an interval each of length n. So as j is subset of I by monotone property, outer measure is less equal outer measure of I. And what is outer measure of j? J is interval, so its outer measure is length. And what is length? Length is n, so n is less equal outer measure of I. So what this gives? This gives that outer measure is greater equal n, and n is any natural number for every natural number. So 1 is less equal outer measure, 2 is less equal outer measure, 3 is less equal outer measure. So we continue in this, we get outer measure must be infinity. So the proof is completed here, and the proof shows that the outer measure of any interval is its length.